Hi, welcome back everybody for the third and last talk of this session. I have pleasure in introducing Kane Townsend, PhD student, University of Sydney, just about ready to do his submission of his thesis pretty soon. Kane's going to talk about Levi subgroups, minimally containing Sylow subgroups in finite groups of Lie type. Thanks, Kane.
Thank you for the opportunity to give a talk today. So yeah, today I'm going to be talking about Levi subgroups minimally containing Sylow subgroups in finite groups of Lie type. But as a sort of preliminary warm-up exercise, we'll look at a similar problem in reflection groups. So a reflection is a linear map with finite order that fixes some hyperplane. And of course, a finite reflection group is a group generated by some reflections. So I've given some examples. The first three are sort of real reflection groups, and you can represent them with these Coxeter diagrams. So what the Coxeter diagrams represent is each vertex you can think of as a generating reflection, and then the edges between two vertices means that the product of those two reflections is order 3, and the no edge between two vertices means those reflections commute. And if you've got a double sort of edge here, that means that the product of those two reflections is order 4. And so I'm going to be mostly focused on the real reflection groups, but I've included the idea of complex reflection groups because I'm going to talk about some Layer-Springer theory, which gives you sort of complex reflection groups from real reflection groups. And so my initial problem is to classify the following, and these are classify the minimal reflection subgroups containing a Sylow L subgroup. And what a reflection subgroup is just a subgroup of W that generates generated by some subset of reflections of W. And then the other question I want to ask is, what are the minimal parabolic subgroups containing a Sylow L subgroup? And a parabolic subgroup, one way you can think about it is, a standard one is if you take some sort of sub-diagram of these Coxeter diagrams by choosing certain vertices and then keeping the edges all the same. And then you can take the conjugates of those. So I've done these classifications, in these references, and the first one for real reflection groups and the second for complex reflection groups. But what I want to say about this classification is that the minimal parabolics, they form a unique conjugacy class just because parabolic subgroups, when they intersect, they form another parabolic subgroup. And these minimal reflection subgroups, they are necessarily contained inside a minimal parabolic. So that sort of gives you an inductive way to classify these problems. So we'll look at a few examples now. Just two quick definitions though. If your reflection subgroup is equal to the minimal parabolic subgroup for some L, then we say that W is L cuspidal and W is L supercuspidal if the minimal reflection subgroup containing a Sylow subgroup is the whole group itself. And so in this example of E6, we have type A4 there, which contains a 5 Sylow subgroup of E6. And of course, you could choose other A4s within the diagram, but these are all conjugate, so there's not too much difference there. And then finally, there's no further sort of reflection subgroups within A4 that would contain a 5 Sylow subgroup. Well, in particular, because A4 has only parabolic subgroups as its reflection subgroups. And then here's a sort of a nice supercuspidal example. So E6, when the prime is 3, is supercuspidal, so there's no sort of reflection subgroups that contain a 3 Sylow subgroup. And then as a slightly different example, F4 when the prime is 3 is cuspidal, but there is a reflection subgroup that contains 3 Sylow subgroup, and this is given by this A2 inside of F4 that you can find by adding on the negative of the highest root and then removing another root, which is known as sort of like the Borel-de-Siebenthal algorithm. So I've done these classifications and I wanted to sort of compare them to a similar problem in finite reductive groups. So we'll introduce some finite reductive groups now. So let GF be a finite reductive group. So G is a connected reductive group over some field of characteristic P. And just to be clear right from the beginning, we want L to be different to P, just so the questions are interesting. And F, I'll let be a Steinberg endomorphism on G. So then we have these standard definitions. We have W is the Weil group of G, which is a type of reflection group with root system phi and simple generating reflections S. And we have this maximally split torus T associated to GF. And we also have this reflection coset of GF, where W is just the Weil group of G, and gamma is the diagram automorphism of the Coxeter diagram induced by the Frobenius map. And then the final sort of definition I want to say is, or notation, is that U alphas are the root subgroups of G. And I've given a simple example here. So GF is equal to GLNQ, and yeah, we've got G given by that GLN, and then we take the qth powers of all the entries and we find the Steinberg endomorphism fixed points of this group and subgroup, and we get GLNQ, which has a Weil group of type A. And just as an example, these are what the root subgroups would look like, something along these lines. So you have ones along the diagonal and some element in one of the other positions, maybe. And so a Levi subgroup is a GF conjugate of this LIF. And this LIF is, you take a group generated by the maximally split torus and U alpha, and the alphas that you choose is some sort of parabolic subsystem of the generating reflections, and then we take the Frobenius fixed points subgroup of this group generated. And yeah, you just want to make sure that the subset I is stable under the action of F. So we can define a similar problem, and that is to classify up to conjugacy the minimal Levi subgroups of GF containing a Sylow subgroup. And these have the similar property as the minimal parabolics in reflection groups, that they will form a unique conjugacy class. And the way that you would go about solving this type of problem is, again, just by understanding order formulas of these groups. So to understand these, you need to know what the generalized degrees of a reflection coset are. So you have these DI, which are the degrees of a set of generating homogeneous polynomials of the ring of W invariant polynomials. And you have these epsilon I, which are the eigenvalues of gamma when they act on these homogeneous polynomials. And so you have these nice sort of formulas for the Weil group and the finite reductive group, GF, in terms of these degrees and generalized degrees. But, and the important point is that this formula here, you can factorize in terms of cyclotomic polynomials on Q. And in particular, if we're talking about a trivial reflection coset, where gamma is 1, all the epsilons are 1. And so we can get this nice formula for the order of GF. So just to simplify things a little bit, we're going to assume that our prime for the Sylow subgroup is not 2, and we're going to focus on the not twisted cases from now on. And I wanted to find this nu sub L as the maximum power of L that divides a number. Then we have a nice fact about the cyclotomic polynomials divisible by L. And those are exactly the ones that have the cyclotomic polynomials divisible by L are those with D equal to this multiplicative order of Q modulo L times some power of L. And in particular, when I is larger than or equal to 1, L only divides these cyclotomic polynomials once. And just straight from that, you are able to show the following lemma, that when the order of Q mod L is 1 for your finite reductive group, then you have this nice relationship between the L divisibility of these quotients of orders of groups. And with that, you are able to show the next theorem that says that the type of minimal parabolic in W is the same as the type of parabolic subsystem associated to the minimal Levi subgroup in G of F. So just a quick example of what this might look like in our E6 and L equals 5 example is, so we have our A4 and we take the products of degrees to find the orders of these groups, and we see that 5 divides once. So our Sylow subgroup is just the cyclic group of order 5. And but then when we go to the finite reductive group setting, when the order of Q mod L is equal to 1, we know that the cyclotomic polynomials divisible by 5 are exactly these ones, and we just need to make sure that these are preserved, which indeed they are, by just calculating based on the degrees. And yeah, so, and then you just check that there's no other sort of parabolic subsystems that will give you a smaller Levi subgroup. So in the cases when the order of Q modulo L is not 1, you start to find that you don't get much of a reduction. And so I thought that maybe you need to do a little bit of extra work on these Levi subgroups or change them up a bit. So that's what we're going to do in the next example. So to do this, we're going to have these regular elements of a reflection coset. And these are sort of introduced by Springer, and then more formally and more generally for Layer-Springer theory. And so a regular element of a reflection coset is an element that has an eigenspace with a vector inside the eigenspace that is not contained in a reflection hyperplane of W. And so furthermore, you have that these regular elements have a maximal eigenspace, where Z to E is eth primitive root of unity. So that's with respect to all elements in this reflection coset, this element is maximal. And there's a nice property that the centralizer of this element is a reflection group on this eigenspace when we have an irregular element. And so what I'm going to do is use this regular element to twist a reductive subgroup of G of F, to twist a reductive subgroup of G, and then take the fixed points subgroup after. And so I've defined this E-twisted subsystem subgroup of G of F. So you take this this subgroup which has the maximally split torus and these root subgroups where psi is just some p-closed subsystem. So I've generalized things from parabolic subsystems to sort of reflection subsystems. And you want to have this nice property that the regular element normalizes these reflection groups generated by the roots in this p-closed system. And then we conjugate by this G, and we get what we call the E-twisted subsystem subgroup when we take the F fixed point subgroup. And the idea behind this is when you have, the idea behind this is when you conjugate the maximally split torus, the order of this group is divisible by phi sub E Q A E. So this is the maximal power of phi sub E, the eighth cyclotomic polynomial that divides G of F. So I've sort of automatically put that cyclotomic polynomial into the order of this twisted subsystem subgroup. And so the problem I ask is classify the minimal E-twisted subsystem subgroups containing a Sylow L subgroup up to GF conjugacy. And first, to get a feel for the problem, we'll do an example. And the example will be inside of E6. So there's a unique 2 regular element in E6, which is the longest element. And the longest element, it acts on these roots of the diagram by sending alpha 1 to the negative of alpha 6, alpha 3 to the negative of alpha 5, and alpha 4 and alpha 2 to the negatives of themselves. So it's the negative of the order 2 diagram automorphism. And then I take a subsystem of type 3A2 given by these roots in the diagram. So I've added in the negative of the highest root. And then we can quickly check that W0 is in this normalizer, just because the roots are getting sent to the negatives of each other or fixed or to the negatives of themselves. But to calculate the order of this twisted subsystem subgroup, we need to understand what the generalized degrees of this reflection coset are. And with the sort of this form, it's not perfect for, say, recognizing straight away what the generalized degrees are, because W0 acts on by sending roots in this simple system to the negatives. So that's not really easy to keep track of. So what you do is you change the representative, and in this case, it's gamma is equal to the longest element of 3A2 times this longest element of E6. And then this will give you the automorphism that's a little bit simpler, because it sends minus alpha 0 to alpha 2, alpha 1 to alpha 5, and alpha 3 to alpha 6. And from that, you can state that the generalized degrees are the following. And from Layer and Springer theory, we can quickly calculate what these groups are. And in particular, I want to pay attention to these factor of 3 that's dividing them. And then since we're looking at a 2 regular element, then it makes sense that we're looking at the cyclotomic polynomials of degree 2 and the second and the 6th cyclotomic polynomials. And you can see that these also preserve like divisibility. And so you can see that 3 divisibility is preserved, assuming that the order of Q mod L is 2. So now I've got the following lemma, which is a generalization in some sense of the previous one, where we've got these quotients of these groups and they have equal L divisibility. And what this allows me to say is a minimal E-twisted subsystem subgroup that contains the Sylow L subgroup directly corresponds to the subsystem that's minimally p-closed, such that we have this normalized property, and this reflection subgroup of this reflection group contains a Sylow of L subgroup. And so this theorem does generalize to the twisted cases. So, but I didn't include that. But yeah, everything sort of works out the same way. So there's nothing too much going on there. And I think that's all I want to say. So thanks for listening.